Hi, everyone. Cool. So thanks for having me here, everyone. I'm Jan. I'm here to talk to you about something I've been working on for the last little while, which we're pretty proud of. It's called Zircuit. It's a new ZK rollup, and we decided to build on top of the OP stack. And today I'm going to share with you some of the messages or some of the challenges that we had in actually doing that. You might hear that it's it's quite easy to do that, and oh, of course you can do that, and you can do that. But it's not necessarily as easy as people might have you believe. And so I'm going to just share some of the challenges. There's going to be a lot of challenges that are omitted on this slide because we've only got so much time to be here. But happy to discuss them with you and discuss ideas in the future. And I'll just tell you about Zircuit as we go through it. So what is an optimistic rollup? At first, when I put the slide in, I was like, maybe people will know, maybe people won't know. After today, I think people will know. But I always like giving a nice, complete talk because I want everything to be self-contained. And ultimately, we're going to be talking about both some level of optimistic rollups and some level of zero-knowledge rollups. So you need to be familiar with these concepts. So an optimistic rollup's pretty straightforward, as you probably know. You get a sequencer, it gets some transactions, either from people using the chain or depositing things on the underlying layer. It sequences them, it constructs blocks, and then eventually there is a state that's output says, after these blocks are executed, this is the state root. And I'm going to try to put this on chain. And if no one says I've done a bad job or slashes me or challenges me, whatever the exact mechanism is for a sufficiently long period of time, like 7 days, that's considered final, and everyone moves on. And this continuously happens over and over again, and eventually you get an L2 chain out of this, which is great. On the other hand, zero-knowledge rollups work almost the same way, except they don't have this awkward finality period, and they have validity proofs. So transactions still originate somewhere, either from the L2 chain itself or from L1 deposits. And then a sequencer still comes along and says, yeah, here are the blocks, let's build them, let's execute some state. But after that step happens, instead of immediately trying to push that state root onto chain, we prove that actually that state transition was valid. And so generally a prover spins up. This is some sort of mathematical magic, which I'll talk a little bit about in a couple of slides, and sort of re-executes it and says, okay, we got the same state root. We also have a proof that I computed it correctly, therefore the sequencer did it correctly, whatever. And then both of those objects get pushed onto chain, both the validity proof that the transition was done and the state root. And therefore, as soon as that stuff hits the chain, there's a verification smart contract that says, actually the validity proof is in fact a validity proof and not just a random string of numbers. And we're all good. We can consider this final, everything works. And so, we were, a bunch of us were researchers and we're playing around with a bunch of ideas with both optimistic stuff and zero-knowledge stuff. And so, maybe we can try to build one on some of these ideas. And so we did. And what we did was build Zircuit. And I'll tell you a little bit about how this came to be on the next slide and why this is sort of titled the OP Stack Challenges. But essentially, we built a ZK rollup which takes a lot of the infrastructure that we get from a lot of the open source optimistic projects, namely Optimism and the OP Stack, and we put in some nice, cool Halo 2 circuits into that framework and system so that we can actually validate the claim that, oh yeah, you can build a ZK rollup on the OP Stack. We're not part of the superchain or things like this, but we are using the infrastructure that we initially get from Optimism with a lot of heavy modifications that we'll talk about during this talk and probably a whole bunch of subsequent talks at various locations. So I'll say also we just launched our testnet 2 days ago. Feel free to check it out, zircuit.com. There'll be links at the end. But that's sort of the short thing. And so I had mentioned that we started this because we wanted to see if this was possible. And that's exactly how this project started. A couple of us had a bunch of grants from the Ethereum Foundation for various things, and we were just looking at all parts of of rollups, and we decided, we're doing a lot of this. There's a lot of really cool stuff we're learning, we're understanding, we're trying to modify, trying to make better, and trying to do differently, right? Maybe not necessarily even optimally, but differently. We want to see if we can actually play around with this. And so we got all these things. We were looking at things like data compression, so we just had a nice talk on data availability, which is great. We thought about ways to analyze the circuitry to make sure that everything is secure in a system like this, and a bunch of things. And we just decided, okay, let's do it. Let's do it really secure, right? Not that other rollups are necessarily insecure or things like this, but we had a security researcher background, and so we wanted to say, what else can we do to add security onto a layer 2? And so Zircuit will be focused quite heavily on sort of a security footing. So we're going to really think about security. And that might sound pretty vague right now, but it'll get a little bit more specific near the end of the talk, I promise. We'll give you some things. In particular, we're going to talk about this idea of sequencer level security, where the sequencer is not just building blocks. Maybe it's doing something a little bit more, something that my colleague Martin had already alluded to if you were here at the beginning of the day. But at the end of the day, after doing all this research, after doing all this work, we sat down, we started writing the code, we started building the product, and here we are. We have Zircuit. So Zircuit's up. It's available for testnet. Please check it out, test it, try to break it, because testnets are there to break things, and give us your feedback, and we'd love to see how this goes. In the meantime, I'm going to slow down, and I'm going to talk to you about what actually needed to be done to make Zircuit into the current thing that it is. So, as I mentioned, we wanted to start building on sort of the best stuff out there, right? Optimism has been around for a while. The OP stack's functioning and it's working. It's working quite great. It's undergoing active development. There's a lot of support for it. And we were playing around with it, and we said, yeah, let's put ZK into it. Everyone says it should be possible, it should be easy. And we get a lot of things almost for free. Not actually for free, as we'll see, but there's a lot of stuff that you don't need to start from scratch with, right? The sequencer exists. The integrations with other parts of the ecosystem exist, right? You can post batches of data onto the L1 right away if you want to. You get that for free. The modifications necessary to a Geth client in order to make something that looks like a rollup also exist, right? We get a lot of things very quickly. As we'll see, it's not always perfect, but or perfect for a ZK VM anyways. But it's a good starting point. On the other hand, there's also people out there like the PSE team working on things like L2 circuits for a ZK VM. And we saw those and said, hey, that's pretty cool. Maybe we can use that as a good starting point to figure out how to make a ZK rollup using the best of these two worlds. There's also probably a dozen other projects out there that are doing both of these types of things individually, right? So there's probably other people working on open source L2 circuits or other circuits for a ZK VM. There's almost certainly other open source optimistic rollup technology out there. But we started with these two because they've been around, they've been mostly functioning, they're pretty solid teams. We wanted to see if we can put them together. And it turns out when you do that, there's a whole bunch of stuff that you need to sort of overcome. So it's not just as simple as 2 Git clones and then spinning it up with a quick make file. There's actually a lot that goes wrong, especially to do it very well, right? So there's a lot of things that go wrong on sort of either side of these components, and then there's a whole bunch of stuff that a rollup needs that you don't get for free, at least not currently. So we have to do a lot of work to overcome these challenges. So for example, on the node infrastructure side, for things like we might get from like the optimistic stack, for example, we have these things like called system transactions that the sequencer puts in, right? And if you're familiar with that ecosystem, you might know what they are. On the other hand, they're sort of designed to be kind of invisible, and they're not talked about. They're not something that most end users care about. Other things like the data availability layer is really nice. There's a batcher, it's pushing batches. Is it pushing the right data? Is it pushing it at the right time? Is it talking to the right other components? I'm sorry, the formatting's a little off on the text. The smart contracts themselves, obviously, arguably one of the most important parts of any rollup, also aren't exactly as modular and easy to use as some people have you believe. They're a pretty good starting point, absolutely. You get to build part of a bridge off of it and things like this. But as we'll see later, it's not just change the proof system. There's a little bit more. The last other thing that's really sort of going to be talked on today is the Geth. So Optimism uses OP Geth, which is a minimally changed version of Geth that they use for their rollup. And then if we switch to the ZK side, a lot is a good starting point as well. We get opcodes, so a good starting point to build our ZK VM, but not necessarily all the precompile. So everything you want maybe isn't there. Moreover, you might get circuits, but not necessarily the means to combine them and actually use them and produce a whole VM. You might get a circuit for KESAC, but not how to glue that into make a VM. It depends on where you look and how you build it. So there's work to be done there, absolutely. And then, of course, you need verification to be done on chain, and generating that isn't necessarily the most up-to-date stuff. In fact, that's probably true of a lot of it. A lot of these people who are working these things have internal ideas, and they haven't pushed code into a nice public repo, or they haven't, spilled the secret sauce, or talked about publicly their ideas, or their stuff to be tested. Even if all of that works, though, you don't have a ZK rollup just yet. There's other infrastructure that needs to be done. So, for example, proving pipelines and things like this, actually generating proofs, making those extra errors on that slide is non-trivial, especially since a lot of this hardware, or a lot of these circuits require hardware that isn't just your laptop. You need a cluster, GPUs, and things like this. And then, there's some really nice stuff, the quality of life that would be great, like good documentation tests, especially like very robust integration tests, and you need front ends and all these other things. But those are less problematic than the sort of core things. So let's take a look at actually what some of the core challenges are that we had in this, and we'll again take a look at the OP stack. I'm not trying to pick on the OP stack, by the way. I think it's a great place to start, but it's not ready for just building a ZK VM very quickly. It takes some effort, and that's what we're here to say. So as I've already mentioned, one of the challenges is it injects these sequencer level transactions. So these are transactions that are included in every block. I got another full slide on this, so I won't talk too much about it, but they're sort of weird, right? From a ZK VM, they're sort of like very, very weird, because for example, they're not paid for. They're free transactions in those blocks, and your circuits sort of start to complain when that happens. Similarly, you're posting data on chain with the OP batcher system if you're choosing to use that, but that doesn't mean it's tied into the circuits in any meaningful way. So you got to do some work to make sure that you're not just burning money posting things onto chain, or if you are doing that, that you have a good reason to do that. The contracts aren't particularly modular. There's a lot of places where you think you can make a change pretty safely, and then other parts break, and I'll talk more about that in a few slides as well. And again, geth was changed, and I think most rollups will need to change geth in some way. But the OP stack changed it in a way that isn't necessarily the best way for a ZK VM to change it. And so, it's a good place to start, but you got to do some work to overcome things. So let's just take a look at one of those specific things, which is deposit transactions. So how do you get L1 ETH onto an L2? Well, you have to do what's called a deposit transaction in the optimistic stack. So you send money to a layer 1 smart contract. The sequencer sort of watching this, deriving it, the op nodes deriving it, and say, oh, look, I saw a deposit. Let me put this on chain. Again, like system transactions, on L2, it's not paid for because users already paid for the gas on L1. So step one is, we have a transaction that is now not sort of well-defined in my circuits if I'm using a really, really clean ZK VM, because now it's not getting paid for. So we got to have some way to overcome that. That's annoying. We can take some steps to overcome that, and that's fine. But even if that is overcome, there's other issues that aren't so sort of easy to catch at runtime. They won't crash sort of the system, but you'll still need to overcome at some point. In particular, one way to deposit ETH onto Optimism is to just send ETH to the Optimism portal contract. And it's got a receive function. It just takes the ETH and sort of emits the event. But it emits the event. It doesn't necessarily track explicitly that, user Jan sent a deposit there. And so when I go to withdraw my transaction now I have to take extra steps to determine if Jan actually made a deposit transaction in the first place, because there's no explicit record, there's no inbox like some other ZK rollups have that say, oh, actually, this user deposited this on chain. The L1 obviously has that transaction in a block somewhere, but doesn't mean the smart contract can query it. And then, of course, doing all of that changes the geth, right? It had to introduce some notion of a deposit transaction, which is actually now pretty common across a lot of rollups, but doing that is not necessarily the way that ZK rollups would do it in the OP stack. So there's definitely a couple more. So let's turn to the smart contracts. We were smart contract researchers with more security researchers, and so we were really concerned about this. We were really looking forward to a contract base that's really modular. To say, there should be a single interface that says prove transaction or prove block or allow transaction, allow withdrawal, sorry. That's not the case. There's at least two out of the box that you'd need to change. So it's not that simple. It's actually a little bit more involved because they have this notion of an inclusion proof, which you may or may not need in a ZK rollup. And then there's a finalization period, which you almost certainly don't need in a ZK rollup. And so changing this takes some effort. And along the way, as you start to make these changes, you start to see that some of the variables that are in those smart contracts are also not necessary. And so you say, oh, okay, I can cut this. This is not an issue. What's a finalization period for a ZK rollup? Well, it's when the thing hits the chain, hits verify. But then you delete the variable and the SDK complains. You're like, oh, okay, so this is actually got some cleanup that would be great. And then if you've been following along the optimism stack, Bedrock came out earlier this year. Up until Bedrock, it wasn't Bedrock. It was whatever pre-Bedrock optimism was. And there's a whole bunch of code that's left over from that state of optimism, and like migrating from that state of optimism to the modern version of Optimism mainnet, which currently exists, and most of that isn't necessary. But some of the code's still there. You don't generally want extra code, so cleaning it up takes some time. And then, of course, there's things like feature incompleteness in the ZK setting. Not the OP setting, but the ZK setting. For example, that explicit inbox recording the deposits that you've done, right? So in order to sort of approve the withdrawals later in a proof, you'd like to have that. On the other hand, there's challenges with generally ZK proofs. I don't think this is a surprise to anyone. In the last couple of years, we've seen a lot of ZK rollups come into the limelight and do some great things. But taking what's out there and trying to put something together very quickly or very functionally isn't particularly easy, right? You might find opcodes, but not necessarily precompiles. Tycho earlier today had mentioned, they even have custom precompiles. There's a lot of work that can be done there. But even if you have all of that, you're almost certainly going to have to aggregate some circuits and put some things together in ways that, is becoming more well documented or understood, but is still very much flexible, right? Your specific rollup and your specific proof system might want to do things in very different ways. In fact, we've taken a novel approach to many others, but there's a lot of ways to do this, and you have to be very careful to do that because there's trade-offs you make. Sometimes it's speed and performance, sometimes it's cost, sometimes it's data, right? So you got to do a lot of these things very carefully in order to get this to work. And so, as I already mentioned, these system transactions are one of those things where the circuits sort of need some little tweaks, even if you look at things that are out there, because these sequencer transactions, system transactions that Optimism gives you look sort of something like on the right. You see that transaction fee is 0, value is 0. Like no one's paying for these in Optimism because they're just system updates, and that's totally fine. And they set really cool values into the L2, right? So it keeps the L2 in sync with the L1. So they're actually kind of necessary in a lot of ways because it ties an L2 block to an L1. So you want to have them. But your circuits don't want to have them this way. They want to interact in other ways, or make trade-offs to do this. So there is some challenge. Other people are doing it in different ways, keeping track of this in the Geth itself rather than the system transactions. But even if you overcome, the sort of disabling payment checks or whatever you need to do to get these included in a block, if you want to prove that block, then one of these transactions in every block. One block every 2 seconds, one transaction per block. That's a lot of extra things you have to prove every block, and it quickly adds up over the years. So it's probably not something you really want to keep, and maybe there's another way to do it, and we're going to be looking into that as well. Of course, even if you have all of those issues solved, just having a ZK EVM and just having a sequencer is not a rollup. You need a whole bunch more that goes on, right? So for example, these prover pipelines, especially if you're not doing it in an open decentralized manner like a proof marketplace, you got to build this. And when there's expensive hardware and cloud things involved, this takes some effort. It takes some real engineering effort to make sure that this is up and this is functioning all the time. You also lack a lot of nice-to-have features. The community is getting really good at benchmarking and testing things across different components, but right now it's still pretty hard to just download a bunch of tests that are very comprehensive for a rollup, whatever that means, right? There's very specific levels of tests we can talk about offline, but testing it is non-trivial. And other things like documentation or web stuff doesn't work, right? We built a new block explorer because we didn't really like or love the ones that are out there, especially for rollups, right? Etherscan's great, but for rollups you have different requirements, and sometimes you need to do things differently. Again, not hating on anyone that's out there, just we're going a different path. In addition to all of that, if you overcome all of that back-end stuff too, which isn't sexy and stuff that no one talks about, there's stuff you want to do to be cool and competitive and sexy. And that is, like new crypto primitives. Folding is relatively new in the ZK EVM world. We'd love to have that brought in. We don't currently have that. Let's see how much, or how hard that will be. There'll be another talk probably about this in a couple of months or a year, or whenever we have the time to talk about it. Things like GPU optimization, all of this needs to come in, right? A lot of this stuff people don't like to share or don't share right away, and we also have our own special sauce. We have GPU engineers who are working on this, and we also want to do this kind of cool stuff. And things like more opcodes if we don't want to be strictly EVM. For now, we are even EVM compatible. In the future, who knows what will come. Precompiles, in-circuit compression, things like this, very interesting. And then on the non-circuit side of things, there's always places to improve as well. Tycho, had a good talk earlier about these other codes, but maybe we want to do other things like additional security features, which I've talked about, and I'll talk about in the next slide. Things like efficient data availability layers, of course. If we want to be super modular, we can do that. We have to look into it. And decentralization, of course, is always on every roadmap. So let's take a look at one of these that are sort of not circuit heavy so that most people in this room can understand it. And we'll take a look at sequencer level security. And so this is one of the ideas that we're pioneering here, where we believe the sequencer can actually be doing a little bit more than just ordering transactions. Maybe we can be a little bit more clever. And maybe it's the case that if we have a nice security threat model and we have a transaction that's going to violate that model for some people who opt into that model, that's the key word, being opt-in, maybe we can do something with that transaction. Now, that's not to say we're going to censor it. We don't want censorship. But it doesn't mean we have to put it in the block in the next 2 hours, right? It can wait a little bit if someone has opted in for this service. This would be something akin to a DeFi circuit breaker, if you've seen those in sort of the DeFi world. But the reality is, once you start playing around with what it looks like to have someone looking at your transactions in the L2 sequencer mempool, you can do a lot. And people are going to be interested in that. Not everyone, and that's why it's going to be opt-in. So for now, if you hit deploy on a testnet, it's just going to work like an EVM. It's going to be fine. Nothing's going to be censored, slowed down, whatever. Be able to flash on all you want on the testnet. But when we go into further steps like the mainnet, we're going to be looking at these features to make people secure, because a lot of people are spending a lot of time to also get the core infrastructure right? Understanding what it means to check that a Halo 2 circuit is correct, or a sequencer is operating successfully. But we believe there's more to security on the rollup, and that is involving the sequencer. So we're going to try that. We're going to see how that goes. And so I'll just end with a little bit of a rollup or a roadmap, for where a circuit is. We just went into to testnet 2 days ago, so that was great. It already went down once, but we fixed it. We set it up again, and over the next year, we're hoping to go into something that's more like a mainnet and come out with real ETH and all of that, and try all these sequencer level security things and involve folding and all these other really cool things into the network and see where we land. So beyond that, we're going to try to continue to do research. This was a research-based project when we started it, before we sort of made it into a real product. But we want to keep looking at research, what's out there, and we want to evolve with the community as long as we do it securely and at the right time. So I think that's about it. But the point is, we built Circuit. It's pretty cool. We did it on the OP stack. It wasn't trivial to do that. There's a lot of stuff that needs to change. And I showed you some of them. There's, like I said, a dozen more that are really technical. I didn't want to involve too much code on the slides, but we can definitely talk about those offline. Feel free to see me out there in the booth. But also we think that there's a whole new paradigm of security and rollups, which is involving other components that are currently overlooked for their roles. So if this role exists, let's involve them in the security process. And in summary, Circuit is a new rollup that we think is greater than the sum of its parts. So thank you. Feel free to reach out to me or come to the booth.
Oops. So thanks, congrats. I mean, always developing a new circuits for ZK-VM is challenging. Were you able to get the precompiles already for testnet working?
No, for testnet, we don't have precompile support right now. So, sorry.
And you're still using, the Merkle tree is using Ketchak, or?
I think it's Ketchak, right?
Did you optimize it somehow?
I don't know. I'd have to check with my engineers on that.
Yeah, I think this approach is very similar to the Chroma I am building, and we are using OpenStack and the Scrolls ZKVM. But last year we planned to start as a ZK rollup, but we failed because the cost, ZK program cost is too much. So could you tell me the current level of the proving cost in the circuit?
Short answer is no, I can't. It's higher than we want it to be by a fair margin. For a testnet, we're also not operating at full proving capability, so the cost estimation is a little bit off. But if you see me offline, we can see about the exact numbers. We have to integrate a lot of our GPU optimizations and get everything on before I tell you a really nice number, especially with the recording on.
Okay. Yeah, I have another question. It's similar, so we have similar plans, and currently the Scrolls ZKVM has aggregation schemes to make a bunch of block proofs to just one. Mm-hmm. So OpenStack just proposed at every 1,800 blocks, so you need to do. If you use the exact same scheme, then how can you do that?
Yeah, so we do have block batching. It's not quite at 1,800 right now, but we do have this paradigm in place. We just need to scale it up. And that's going to be an incredible challenge. I'm not going to tell you, say, we can aggregate 1,800 blocks right now, but it is on the roadmap. So we have sort of this notion of an OP block and then, another ZK-proved block. But the goal is to eventually get them to one-to-one. And maybe there's a chance in 3 months I'll be giving a talk how that didn't work out. But that's the idea.
Thank you.
Does hybrid imply that you can withdraw using the 7-day withdrawal period and with the ZK?
No, the only hybrid is from the architecture itself. It's a ZK rollup. So as soon as the proof containing your block hits the chain and is verified, you're good to go. Yeah. So
Got it.
Matter of hours on testnet and much less ideally in mainnet.
Anyone else? All right. Thank you, Jan.
Thank you.